The 88mm flak gun crew had rehearsed their timing to perfection. From aircraft detection to first shot, 11 seconds. The loader could slam a 21-pound high-explosive shell into the breech in 3.2 seconds. The traverse operator could track a bomber at 250 miles per hour, with hand wheels calibrated to milliradian precision. What Unteroffizier Klaus Ritter and his gun crew outside Anzio could not rehearse was the physics of an artillery shell that thought for itself. On the 22nd of January 1944, the first American 105mm howitzer rounds equipped with the M48 proximity fuse began falling on German positions along the Gustav Line. The shells detonated 70 feet above the gun pits, not on impact. The fragmentation pattern that followed rewrote every assumption about artillery warfare that had held since the Napoleonic Wars. Ritter's crew, dug into reinforced positions that could withstand direct hits, died without the shells ever touching ground. The trench walls that protected them from impact fuses became killing chambers when shrapnel rained vertically downward at supersonic velocity. Traditional impact-fused artillery required direct hits or near misses to be effective against entrenched positions. German doctrine, refined through 4 years of Eastern Front combat, emphasized deep foxholes with overhead cover. A shell had to land within 5 meters to guarantee casualties against a properly dug-in infantry section. At 10 meters, the lethal radius dropped to roughly 30%. At 15 meters, fragmentation became survivable for prone troops. These calculations had governed artillery tactics since 1914. The proximity fuse eliminated distance entirely. It detonated at optimal height automatically, creating a lethal fragmentation cone that covered a circular area 5 times larger than an impact-fused round. A 105mm shell with an M48 fuse, set to detonate at 20 to 30 feet altitude, created an effective casualty radius of 40 meters against troops in open trenches. The mathematics of survival inverted catastrophically for defenders who had spent weeks fortifying positions against the wrong threat. The German 88mm Flak 36, arguably the finest anti-aircraft gun of the war, could send high-explosive shells to 26,000 feet altitude. Its optical predictors could calculate lead angles for targets moving at closing speeds of 400 miles per hour. At Anzio, these guns formed the backbone of German defensive fires, positioned in carefully surveyed positions with interlocking fields of fire. Each gun represented 2,000 man-hours of engineering and 5 tons of precision steel. None of it mattered when American shells began detonating at the mathematically perfect height to saturate trenches with fragmentation. Oberst Friedrich Weber, commanding German artillery in the Anzio sector, recorded his assessment in the 14th Army War Diary on January 24th. Enemy artillery demonstrates new fusing mechanism. Shells burst at height of 20 to 30 meters without contact. Effect against personnel in open positions. Catastrophic. Casualties triple our estimates. Recommend immediate overhead cover for all forward positions. The recommendation was sound. Implementation was impossible. Constructing overhead cover for thousands of meters of trench line required timber, corrugated steel, sandbags, and most critically, time. Materials that the Wehrmacht, strangled by Allied air superiority and partisan interdiction, could not deliver to forward positions. Even where materials existed, construction drew immediate counter-battery fire. The proximity fuse had created a tactical checkmate. Troops in open trenches died from airbursts. Troops building overhead cover died from observed artillery. Troops abandoning positions died from infantry assault. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The M48 fuse, officially designated Bomb Fuse VTM48, contained 5 miniature vacuum tubes, a battery with 200-second active life, and a radio transmitter operating at 180 MHz. The entire assembly measured 2.5 inches in diameter and weighed 1.5 pounds. It survived 20,000 grams acceleration forces when fired and remained functional through ballistic trajectories, reaching temperatures of 150 degrees Fahrenheit from air friction. The fuse transmitted continuous radio waves downward. When reflected, waves returned with sufficient strength, indicating ground proximity of 20 to 30 feet. A thyrotron tube fired the detonator. German intelligence recovered intact Fuzes from duds by February 1944. Photographs and technical analysis reached Berlin within a week. The complexity staggered German engineers. The smallest vacuum tubes in German production measured nearly double the diameter of the American components. The idea of making these tubes survive artillery launch seemed fantastical. The notion of producing them in quantities sufficient to equip every artillery shell verged on impossible. Wehrmacht technical intelligence estimated American production capacity at perhaps 5,000 fuses monthly. The actual figure by January 1944 was 400,000 fuses per month, with production accelerating. The Eastman Kodak plant in Rochester produced tubes. The Zenith Radio Corporation made transmitter assemblies. Crosley Corporation assembled complete fuses. The entire proximity fuse program represented an industrial mobilization that matched the Manhattan Project in complexity, while receiving a fraction of historical attention. At Anzio, the initial stockpile of VT-fused ammunition was restricted to defensive fires only. Supreme Allied Command feared premature German recovery and replication if fuses fell into enemy hands in offensive operations. The restriction lifted within 72 hours when the desperate German counterattacks made conservation impossible. On January 28, American artillery battalions supporting the beachhead fired 12,000 proximity-phased rounds in a 6-hour period during a major German assault near the factory district. The German 362nd Infantry Division, attacking across open ground toward American positions, encountered artillery that seemed to anticipate their movement. Shells burst continuously at 70 feet altitude, carpeting approach routes with fragmentation that shredded flesh through winter uniforms. Wehrmacht after-action reports described casualties at 40% before units reached jumping-off positions. The attack collapsed before engaging American infantry. Survivors described the experience as advancing through a steel blizzard that fell from empty sky. Lieutenant Ernst Bauer, recovering from shrapnel wounds in a field hospital near Albano, gave testimony that appeared in intelligence summaries. The shells explode over your head before you hear them coming. There is no warning, no whistle, just the crack of detonation and the whip sound of fragments cutting air. Men beside me fell with wounds in the top of their heads, their backs, their shoulders, all the places that a foxhole protects. We could not dig deeper than the sky. German infantry had learned to take cover when artillery fire began. Experience taught men the sounds and timing that preceded impact. A high trajectory 105 mm round made a distinctive flutter sound in the final seconds of flight. Troops had perhaps 2 seconds to press into earth before impact. The proximity fuse eliminated this warning entirely. Shells detonated while still invisible, still silent, with no cues that allowed even veteran soldiers to seek protection. German counter-battery radar, among the finest in the world, could track American shells in flight and provide firing coordinates for counterfire. At Anzio, this technical advantage produced minimal results. American artillery battalions displaced immediately after fire missions, relocating before German counter-battery rounds arrived. The Wehrmacht's superior position-finding capability meant nothing against an enemy whose artillery could kill from positions too far back to effectively counterattack, while conserving ammunition and maintaining continuous fire through rapid displacement. The 105 mm M2A1 howitzer, standard equipment for American divisional artillery, could fire 4 rounds per minute with a trained crew. Each battalion fielded 12 guns. A standard fire mission against German trench positions involved 72 rounds, impacting within a 200-meter square in less than 90 seconds. With proximity fuses, this created an steel umbrella that made survival in open positions essentially random chance. German units reported 60–70% casualties from artillery alone during major American fire missions, rates previously associated only with sustained ground combat. What made the proximity fuse strategically decisive at Anzio was not just its lethality, but its effect on German tactical flexibility. Wehrmacht doctrine emphasized aggressive counterattacks and rapid repositioning to prevent Allied breakout from the beachhead. These movements required troops to exit protected positions, advance across open ground, and concentrate for assault. Every phase became a killing zone when American forward observers could call artillery that detonated at optimal height without requiring direct hits. The German response evolved through desperate experimentation. Attacks shifted to night operations when American artillery observation was degraded. Movement occurred in dispersed small groups, rather than formed units. Troops fashioned crude overhead protection using doors, sheet metal, logs, anything to create barriers against downward fragmentation. None of these measures restored the tactical mobility that Wehrmacht operations required. The proximity fuse had effectively pinned German forces in position. By February 15th, German casualty reports from Anzio showed artillery accounted for 64% of total casualties, compared to historical averages of 40% in previous Italian campaigns. The shift represented not increased American artillery ammunition expenditure, but rather dramatically improved effectiveness per round fired. Each proximity-fused shell produced casualties equivalent to 4 conventional impact-fused rounds. The Americans were essentially multiplying their firepower by 4 without adding a single additional gun. Generalfeldmarschall Albert Kesselring, commanding German forces in Italy, recognized the strategic implications immediately. In communications with Oberkommando der Wehrmacht, he noted, "American proximity fuse has fundamentally altered artillery effectiveness. Our defensive positions provide minimal protection. Cannot sustain current casualty rates without replacement divisions which do not exist. Recommend elastic defense in depth, but terrain constraints at Anzio make this impossible." The proximity fuse had created a tactical problem for which German doctrine had no adequate answer within the constraints of the Italian battlefield. The numbers told the story with mathematical precision. In January 1944, before widespread VT fuse deployment, American forces at Anzio fired an average of 95 rounds per German casualty. By March 1944, with proximity fuses standard for 105 mm and 155 mm artillery, the figure dropped to 24 rounds per casualty. The improvement represented a 75% increase in artillery effectiveness, achieved through fuse technology alone, requiring no changes in guns, ammunition stocks, or tactical doctrine beyond target selection. What German gunners never imagined on the 7th of December 1941, when the proximity fuse program began crash development, was that American industrial capacity could miniaturize vacuum tube technology, ruggedize it for artillery launch, and manufacture it in quantities that made single-use disposable electronics routine. The same nation that had made automobiles affordable through assembly line mass production had applied identical principles to guided ammunition. The result was a weapon that made every artillery shell think, aim, and choose its moment of maximum lethality. The trenches that had protected soldiers since the Western Front became obsolete overnight, and German forces discovered they were fighting a war where the sky itself had become hostile. The National Defense Research Committee meeting on the 8th of May 1940 lasted 17 minutes. Dr. Merle Tuve from the Carnegie Institution presented the theoretical framework for a radio proximity fuse. The concept was simple enough for undergraduate physics. Transmit radio waves downward from the nose of an artillery shell, measure the reflected signal strength, detonate when reflection indicated optimal altitude. What wasn't simple was building vacuum tubes that could survive 20,000 times the force of gravity when a howitzer fired, function reliably through 6,000-foot altitude changes in 30 seconds, and cost pennies to manufacture by the millions. British researchers at the Telecommunications Research Establishment had attempted similar development in 1939. Their conclusion, delivered to the War Office in January 1940, stated that miniature vacuum tubes capable of surviving artillery launch were theoretically possible, but practically impossible to manufacture in quantities sufficient for military use. The assessment was technically correct. What British engineers had not accounted for was American industrial capacity operating without resource constraints or manufacturing traditions that prioritized handcrafted precision over mass-produced adequacy. The Proximity Fuse program assigned the cover designation VT for variable time to disguise its actual function, received $5 million in initial funding, and a deadline of 18 months to deliver a working prototype. The budget would eventually reach $27 million, equivalent to roughly $500 million in 2024 dollars, before the first combat-ready Fuzes reached operational units. For comparison, Germany spent approximately $12 million on all proximity fuse research, between 1,939 to 1,945, never producing a combat-ready design. Dr. Tuve's team at the Applied Physics Laboratory identified 5 fundamental engineering problems that had to be solved simultaneously. First, vacuum tubes small enough to fit inside a fuse body 2.5 inches in diameter. Second, battery technology that could provide stable current for 200 seconds while experiencing acceleration forces that would shatter conventional battery construction. Third, a radio transmitter circuit simple enough to be assembled by semi-skilled labor at rates exceeding 1,000 units per day. Fourth, fuse components that could be manufactured from readily available materials without requiring exotic alloys or specialist production equipment. Fifth, and perhaps most critically, a design that could be standardized across multiple manufacturers without requiring custom tooling or precision machining beyond ordinary American machine shop capability. The vacuum tube problem alone consumed 8 months of development. Western electric engineers redesigned traditional tube construction from first principles. Instead of glass envelopes with separate element assemblies, they developed a single-piece ceramic tube body with elements inserted through the base and sealed with molten glass in a continuous production process. The tube measured 0.4 inches in diameter and 1.2 inches in length, roughly 1/3 the size of the smallest commercial tubes then available. Raytheon Manufacturing Company, producing similar tubes for testing, achieved the critical breakthrough in shock resistance. Traditional vacuum tubes mounted their internal elements on fragile wire supports that would shatter under artillery acceleration. Raytheon engineers embedded the elements directly into ceramic supports, creating a rigid structure that distributed launch forces evenly across the entire tube body. The resulting tubes survived 20,000 grams testing with 97% reliability, well within military specifications. Battery development followed an equally unorthodox path. Conventional batteries used liquid electrolytes that would splash and short-circuit under launch acceleration. The naval research, preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. Laboratory developed a reserve battery using dry electrolyte salts kept separate from electrodes by a thin diaphragm. At launch, the acceleration force ruptured the diaphragm, mixing electrolyte and electrode to activate the battery. The design was self-activating, required no external power source, and provided stable current for precisely the duration of a typical artillery shell's flight from launch to impact. By December 1941, the Applied Physics Laboratory had working prototypes that functioned under laboratory conditions. Actual artillery testing revealed problems that laboratory simulation had not predicted. Shells tumbled in flight due to manufacturing tolerances in shell bodies. Tumbling caused the radio transmitter to lose ground reflection entirely when the fuse pointed sideways or upward. The solution required redesigning the transmitter antenna to maintain ground contact regardless of shell orientation, essentially creating an omnidirectional broadcast that could receive reflections from any angle. Temperature presented another unexpected challenge. Artillery shells reached external temperatures of 150 degrees Fahrenheit from air friction during flight. Internal fuse components, insulated by the steel shell body, experienced slower heating, but still exceeded the operating temperature range of standard electronic components. Every resistor, capacitor, and wire connection required testing at elevated temperatures to ensure the fuse remained functional from launch through detonation. Components that performed perfectly at room temperature failed catastrophically at 120 degrees Fahrenheit. The entire parts inventory had to be recertified for high-temperature operation. The transmitter circuit itself went through 17 design iterations before achieving the required reliability. Early versions used traditional superheterodyne receivers that were too complex for mass production. The final design used a super-regenerative receiver circuit with just 5 tubes total, simple enough that semi-skilled workers could assemble complete fuses without requiring electronics training. The circuit drew 20 milliamps, well within the battery's capacity, and generated sufficient transmission power to receive ground reflections from 70 feet altitude. Production scaling began in April 1942, when contracts went to multiple manufacturers simultaneously. Eastman Kodak received contracts for vacuum tubes. Crosley Corporation tooled up for fuse assembly. Zenith Radio produced transmitter components. General Electric manufactured batteries. The program deliberately avoided concentrating production in single facilities, recognizing that German intelligence would eventually discover the fuse's existence and potentially target manufacturing sites. The first combat-ready fuses, designated M48, completed testing in August 1942. The Navy received initial production for anti-aircraft use aboard warships. Army artillery waited until January 1944, partly due to production allocation priorities and partly due to security concerns about fuses falling into German hands in ground combat, where recovery was more likely than from naval engagements in open ocean. What made American mass production of proximity fuses possible was not superior engineering, but rather industrial systems thinking. German engineers, examining captured fuzzes, produced technically superior designs with better radio sensitivity and lower power consumption. These designs required precision machining to tolerances of 0.001 inches, assembly by skilled technicians, and components manufactured from specialized materials. German. Industry could produce perhaps 500 such fuses monthly. American industry. Accepting slightly lower technical performance in exchange for simplified manufacturing, produced 400,000 fuses monthly by January 1944. The Crosley Corporation plant in Cincinnati exemplified this approach. The facility employed 4,000 workers, 60% of them women with no prior electronics experience, assembling fuses on a moving production line adapted from automobile manufacturing. Each worker performed a single operation, inserting tubes, soldering connections, testing circuits, installing batteries. The entire fuse assembly required 17 individual operations, taking approximately 4 minutes total. Daily production reached 15,000 fuses by mid-1944, with defect rates below 2%. Quality control relied on automated testing rather than individual inspection. Every fuse passed through a testing station that verified radio transmission, battery voltage, and electrical continuity. Fuses that failed any test were rejected, automatically without human judgment required. The testing equipment itself was simple enough that maintenance could be performed by factory electricians rather than electronics specialists. The entire system was designed around the assumption that components would fail occasionally, and that catching failures through testing was more efficient than preventing them through precision manufacturing. Cost per fuse dropped from $732 for initial prototypes to $18 for production models by late 1944. The decline reflected both manufacturing efficiency improvements and negotiated volume discounts with component suppliers. At $18 per fuse, the proximity fuse cost roughly twice as much as a conventional impact fuse. But since each proximity-fused round produced casualties equivalent to 4 conventional rounds, the economic calculation favoured VT Fuzes decisively. American artillery could achieve the same tactical effect with half the ammunition expenditure and 1/4 the shipping burden. German attempts at replication revealed how completely American production methods had diverged from European manufacturing tradition. The Telefunken Company received contracts in March 1944 to develop a German proximity fuse. Their engineers produced a working prototype in 6 weeks, technically superior to the American M48 in every measurable specification. Production estimates indicated Telefunken could manufacture 2,000 fuses monthly, requiring allocation of skilled workers from radar production and components from existing stockpiles. The program was cancelled in July 1944, when it became obvious that diverting resources from radar and communications equipment would cause greater operational damage than 2,000 proximity fuzzes monthly could. Offset. The Soviet Union received 100 sample M48 fuses under Lend-Lease in February 1944 with technical documentation. Soviet engineers examined the design and requested additional samples rather than attempting domestic production. Post-war, Soviet analysis concluded that their electronics industry lacked the production capacity to manufacture miniature vacuum tubes in sufficient quantities to make proximity fuse production militarily significant, before 1947 at earliest. The Americans had created a weapon that required not just technical knowledge, but industrial infrastructure that took years to develop. What the proximity fuse demonstrated was that modern warfare had evolved beyond weapons design into production system design. The side that could manufacture adequate weapons in overwhelming quantities had decisive advantage over the side that manufactured superior weapons in limited numbers. German 88mm guns were technically superior to American 105mm howitzers in range, accuracy, and versatility. But American industry produced 10,500 105mm howitzers between 1941 to 1945, compared to 8,000 German 88mm guns. When each American howitzer fired shells that were 4 times more effective per round, the mathematical advantage became insurmountable. By June 1944, proximity fuse production reached 500,000 units monthly. By December 1944, production hit 700,000 monthly. By March 1945, American artillery in Europe was firing proximity-fused ammunition as standard for all missions against troop concentrations, field fortifications, and area targets. The transition from specialized experimental weapon to routine standard ammunition took just 14 months, a timeline that reflected both production capacity and tactical confidence in the technology. The fuse production program employed 28,000 workers across 14 primary manufacturing facilities and 67 component suppliers. For comparison, the Manhattan Project employed approximately 125,000 workers at peak. The proximity fuse received far less historical attention, but arguably had more immediate tactical impact on the war's outcome in Europe. Every artillery battalion that received VT-fused ammunition saw its effectiveness multiply by a factor of 4, without requiring additional guns, crews, or training beyond basic target selection procedures. German soldiers, dying under airbursts that arrived without warning, never knew they were experiencing the fruits of an industrial mobilization that had transformed vacuum tube technology from laboratory curiosity to disposable artillery component. The same mass production techniques that made radios affordable for consumers made proximity fuses affordable for military use. American industry had taken laboratory science, stripped it down to essential functionality, and manufactured it in quantities that made single-use electronics routine. The German gunners, who never imagined shells that thought for themselves, were victims not of superior engineering, but of superior production systems operating without resource constraints. The future of warfare was being written in Cincinnati, Rochester, and Chicago, where assembly lines turned scientific theory into artillery shells at rates that traditional European craftsmanship could never match. The Battle of the Bulge began on the 16th of December 1944, with German artillery preparation that lasted 90 minutes. 500 guns from 3 panzer armies fired 10,000 shells into American forward positions along an 80-mile front in the Ardennes. The barrage was meticulously planned, hitting command posts, communications nodes, and artillery positions identified through weeks of reconnaissance. By 8:30 a.m., German infantry advanced through gaps torn in American lines by what Oberst Otto Skorzeny called the most effective artillery preparation since the Somme offensive of 1918. At 11 a.m., when fog lifted enough for forward observers to identify targets, the 333rd Field Artillery Battalion, supporting the 106th Infantry Division, fired 480 rounds in the first 20 minutes. Every shell carried an M48 proximity fuse. German infantry, advancing in company-strength formations towards Street Vith, encountered artillery that detonated continuously at 70 feet altitude, creating fragmentation patterns that killed troops in drainage ditches, behind stone walls, and in shallow scrapes that would have protected them from conventional impact fuses. Grenadier Hans Vollmer, 18th Volksgrenadier Division, survived the initial barrage and recorded his experience in a diary recovered by American forces in January 1945. The shells burst over our heads before we could hear them falling. Men dropped without wounds visible from the front. All the shrapnel entered from above. We tried to spread out, but the explosions covered too much ground. My company began with 140 men. After 30 minutes, we counted 51. We had not yet seen American infantry. The Wehrmacht had planned the Ardennes offensive, assuming artillery would be degraded by weather conditions that prevented aerial observation. The proximity fuse eliminated this calculation entirely. Forward observers required only approximate target coordinates. The fuse automatically detonated at optimal height, regardless of terrain, vegetation, or ground conditions. A conventional artillery mission against troops in a wooded area required forward observers to adjust fire until shells burst in the trees above targets. Proximity fuses burst at the correct height on the first salvo, requiring no adjustment fire that telegraphed American artillery positions. The 7th Armoured Division, holding the critical road junction at Street Vith, received support from 4 battalions of 105mm howitzers and 2 battalions of 155mm guns. Total tubes, 90. These guns fired an average of 40 rounds per gun per day between December 16 to 23, roughly 3,600 rounds daily. With proximity fuzzes standard on 80% of missions, American artillery created a continuous steel curtain around Street Vith that German infantry could not penetrate without catastrophic casualties. German casualty reports from the Street Vith sector show 2,847 artillery casualties between December 16 to 20, compared to 1,934 small arms casualties. The ratio was unprecedented in Wehrmacht experience. Historically, small arms fire caused 60% of infantry casualties, with artillery accounting for 40%. The proximity fuse had inverted this relationship completely. German soldiers were more likely to die from artillery they never saw than from rifles they could shoot back at. The psychological impact manifested in unit cohesion degradation. German infantry, who had demonstrated extraordinary aggression in the offensive's first days, became increasingly unwilling to advance across open ground after experiencing proximity-fused artillery. Tactical doctrine emphasized that artillery fire, while dangerous, could be endured by well-trained troops maintaining dispersion and moving rapidly between covered positions. This doctrine assumed shells had to impact ground or obstacles to detonate. When shells detonated automatically at optimal height, maintaining movement under fire became psychologically unsustainable. Hauptmann Friedrich Linge, commanding the TI Battalion, 294th Infantry Regiment, submitted after-action reports that reached Army Group B headquarters on December 22. American artillery demonstrates new fusing that makes conventional dispersion tactics ineffective. Casualties during movement approach 50% in some companies. Troops increasingly reluctant to leave covered positions. Request clarification on tactical doctrine for advancing under this fire. No clarification came because no effective doctrine existed. The Wehrmacht had not developed tactical responses to proximity-fused artillery because German intelligence had underestimated American production capacity by a factor of 40. Intelligence estimates in November 1944 suggested American forces might have 50,000 to 100,000 proximity fuses available for major operations. Actual stockpiles exceeded 4 million fuses by December 1944. American artillery was firing VT-fused ammunition as standard rather than as a specialized munition, reserved for critical missions. The Battle of the Bulge consumed American proximity fuse stockpiles at rates that staggered logistics planners. The First Army alone fired 1.2 million artillery rounds between December 16 to 31, with approximately 400,000 carrying proximity fuses. The Third Army, swinging north to relieve Bastogne, fired an additional 800,000 rounds, with 250,000 proximity fused. Total VT fuse expenditure in the Ardennes exceeded 650,000 rounds in 2 weeks, more than the entire German ammunition production for all artillery types in the same period. What made this expenditure strategically decisive was not just the immediate casualties, but the operational tempo disruption. German planning for the Ardennes offensive assumed infantry could advance 3 to 5 kilometers per day against determined American resistance. The proximity fuse reduced this to 500 to 800 meters per day in sectors where American artillery could bring concentrated fire. The entire offensive timeline, premised on reaching the Meuse River within 5 days, became impossible when forward progress slowed to 1/6 of planned rates. The 2nd Panzer Division, spearhead of the northern penetration, advanced 45 kilometers in the first 3 days exactly on schedule. Between December 20 to 24, as American artillery reinforcements arrived and ammunition stockpiles rebuilt after initial depletion, the 2nd Panzer Division advanced 8 kilometers while taking 2,300 casualties. The division's final position near Celles, 4 miles from the Meuse River, represented the high water mark of the German offensive. American artillery from 3 divisions concentrated fire on the salient, firing VT-fused ammunition at rates exceeding 100 rounds per gun per day. Survivors from the 2nd Panzer Division described the experience of being caught in this fire as uniquely terrifying. Obergefreiter Paul Schiffer, interviewed after capture on December 26, stated, "The shells explode continuously above you. There is no pattern, no rhythm. Just the crack of detonation and the whip of steel fragments cutting air. You cannot predict where it is safe. Men in foxholes die. Men behind vehicles die. Men in buildings die when fragments punch through windows and doors. The only safety is to not be there." The thunder that fell from empty sky around Celles on Christmas Eve, 1944, involved 3 American artillery battalions firing 4,400 rounds in 6 hours. With proximity fuzzes set for 70-foot altitude detonation, the barrage created a lethal zone covering approximately 2.5 square kilometers. German forces in the salient, trapped between American artillery and advancing armor, suffered 60% casualties before withdrawal orders arrived. The 2nd Panzer Division, which had begun the offensive with 12,500 men, counted 4,800 effectives on December 27. The proximity fuse's impact extended beyond direct casualties to logistics and command disruption. German supply columns, advancing on roads within range of American artillery, took casualties that prevented forward delivery of fuel and ammunition. Command posts located in villages or farm buildings became death traps when VT-fused shells burst overhead, sending fragments through roofs and walls. Wehrmacht doctrine emphasized forward command to maintain tactical control. The proximity fuse made forward command catastrophically dangerous. At Bastogne, the 101st Airborne Division held the town with support from the 969th Field Artillery Battalion's 155mm howitzers. These guns, firing 95-pound shells with proximity fuses, created a defensive barrier that German forces could not breach despite surrounding the town completely. The 155mm VT-fused round, detonating at 70 feet altitude, produced a casualty radius exceeding 60 meters. 3 shells, properly spaced, could sterilize a football field of exposed personnel. German attacks on Bastogne between December 20 to 26 repeatedly stalled 200 to 300 meters from American lines, unable to close to assault distance through artillery fire. German artillery responded with counter-battery fire using conventional impact fuses. The asymmetry was mathematically stark. American forward observers could direct fire on German troops, advancing across open ground, achieving casualties with every mission. German observers directing fire on dug-in American positions required direct hits or near misses to inflict casualties. The proximity fuse had created an artillery advantage equivalent to fighting an opponent armed only with smoothbore muskets while carrying rifled firearms. By December 26, when Patton's Third Army made contact with Bastogne defenders, German forces in the Ardennes salient had lost operational momentum entirely. The proximity fuse, combined with American numerical superiority in artillery tubes and ammunition, had created conditions where German infantry could not advance, could not hold captured positions under counter-battery fire, and could not withdraw without taking casualties from pursuing American artillery. The offensive that was supposed to reach Antwerp and split Allied armies had culminated 60 miles short of the Meuse River. The final accounting of the Battle of the Bulge showed proximity-fused artillery had caused approximately 30% of all German casualties, roughly 25,000 of the 82,000 total German casualties recorded. For comparison, American artillery using conventional fuses in the Normandy campaign had caused approximately 15% of German casualties. The effectiveness improvement represented not just better fusing, but a fundamental change in artillery's battlefield role, from suppressive fire requiring multiple missions to achieve results into precision area denial weapon that delivered casualties on first firing. What German gunners never imagined when they fired the opening barrage on December 16 was that American artillery would respond with ammunition that made every shell a precision-guided munition. The proximity fuse had not changed artillery range, accuracy, or explosive power. It had changed the fundamental relationship between artillery and infantry by eliminating the protection that entrenchment provided. Foxholes, trenches, and hasty defensive positions that had protected soldiers since World War I became obsolete. The vertical dimension of warfare had opened, and German forces discovered they had no defense against shells that fell from empty sky with perfect timing to maximize casualties. The thunder of American proximity-fused artillery became the soundtrack of German defeat in the Ardennes. Not because American guns were superior German 88mm and 105mm artillery pieces matched or exceeded American howitzers in technical specifications. The defeat came from American industry's ability to take vacuum tube technology, miniaturize it, ruggedize it, and manufacture it in quantities that made single-use electronics routine. By January 1945, proximity fuse production exceeded 700,000 units monthly. Germany's entire electronic industry could not have matched this production if dedicated entirely to fuse manufacturing. The thunder that fell from empty sky was the sound of American industrial capacity translated directly into battlefield advantage. German soldiers heard it, died from it, and never stopped it. Because wars are not won by superior weapons. They are won by superior production systems, manufacturing adequate weapons in overwhelming numbers. And in that contest, American industry had no peer.